everybody.
Hi.
I can start this like I start my videos for geometry. Hey y'all. I don't know how to start them.
How's it going, guys?
How do you start talking to a computer screen?
How's it going?
Hey y'all.
My name.
Mr. Picker here.
Yeah, I'm doing yours. You can't say y'all.
So we're going to talk about conditional probability. So when we talk about regular probability, we could write, like, if I had a coin and I flipped it, I could write, what's the probability of getting heads? Okay, that reads probability of heads. When we write a conditional probability, we're going to have two events. I want to know the probability of something happening given that something else has already happened. So we would write a conditional probability like this. What is the probability of event B happening given that event A has already happened?
So, like, school being canceled of snow?
Yeah, so what's the probability of having no school given that it snowed? Probably 100%. So, for example, I have a deck of 52 cards. I have a deck of 52 cards. I'm going to draw 2 cards, and I'm not replacing the first card. So I draw a card, look at it, and draw another card. I want to find the probability that on the second card I draw a queen, given that I've drawn a king the first time around. So when I go to draw the queen, how many cards are left? 51. How many ways can I get a queen? 4. Is it affected by the king? No.
Wait, so which one's okay?
Yes. Probability of getting a queen given that I've drawn a king. So the probability changes based on the first event. So this is a conditional probability. It's a probability based on getting a king initially and then not putting the card back in the deck the second throw. So this is just another way to look at these. So there's this study being done on children. They're testing if they have this special gene. I don't know what it's called. They either have the gene or they don't. And then they test their IQ. And they look at the kids who have a high IQ and the kids who have a normal IQ. So first of all, what's the probability that one of the kids has a high IQ?
33 out of 72. 11. Oh. 52 out of 102.
52 out of 102. There's 52 students or children with a high IQ, and there's 102 total. I realize as I write that, it might look bad. High IQ. So that's a regular probability. Let's look at a conditional probability in this example. What is the probability that a student has a high IQ given that they have the gene? So probability of a high IQ given that they have the gene. I'm going with the 33. 72. So I will answer the phone. And sure. And 161. No. Back. I don't know what that is. So we're given that the child has the gene. So we're in that world. There's 33 children with the gene who have a high IQ out of a total of 72 children that have the gene. So that's our new probability. So this is the probability of just having a high IQ. This is the probability of having a high IQ, given that you also have this special gene that they're looking at. So you can see the probabilities change. Just like the probability change for drawing the queen after we've already drawn a king. But Jones? Cool. Independent events are events which don't influence each other's probability. So we just did examples using dependent events. So if two events are independent, then they're conditional probability. So the probability of event B happening given that event A happened is going to be the same as just the probability of event B happening. So the condition in an independent event does not influence the probability of the other event. That's a little abstract. Let's do an example. This time, I'm going to select two cards. I select a card, I look at it, then I put it back in the deck. What's the probability I select a queen then? 4 out of 52. I put the cards back, so drawing the first card does not affect the second event. So the probability of drawing a queen is the same as it would be on the first try.
Probability of.
Yeah. Yeah, if I asked you for the probability of drawing the queen, given that you drew a king and replaced it, you could just write probability. All right, so let's talk about whether or not events are independent or dependent. Tossing a coin and then rolling a six-sided die. They're independent. The coin flip is not going to determine what you get when you roll the die. There's some in here that I like because it's sort of public service announcements. Driving over 85 miles per hour and getting in a car accident. They're very dependent. Okay? So the faster you drive, the more likely you are to lose control and an accident. Let's do one more public service announcement. Smoking a pack of cigarettes per day and developing emphysema, a chronic lung disease. Dependent.
Did I smoke a pack a day and I was at the
How about exercising frequently and having a 4.0?
Independent.
Independent. Okay. I started putting on weight the summer I got a 4.0. So my fitness did not determine my grade point average. Questions about independent versus dependent? Is this better than just a bunch of words on the screen?
Yes.
Cool. We got to do some words though. So if we have two independent events, one does not influence the probability of the other happening. Flipping a coin, rolling a die. The probability of both of them happening in sequence is just the probability of A times the probability of B. So I think that's something you already knew, or at least had a good feeling about. So let's do the example. Probability of flipping a heads and getting a 3 on a die. Yeah, it's like a multiplication dot, sorry. It was kind of an afterthought.
1/2 times 6.
Yeah, so the probability of getting ahead is 1/2, 3/6.
Oh, 1/6.
1/6. Probably getting a 3 is 1/6. So the probability of getting ahead and a 3 is 1/12. We've kind of already done that. Drew a tree diagram, found a sample space. There's one way to get ahead in a 3. If I have dependent events, we're going to need something different. I'm not sure. So this is, if I have two dependent events, the probability of getting A and B happening is the probability of A, the first event, times the probability of B given that A has already happened. just a quick side note. If I say with replacement, that makes something independent. If I say without replacement, that makes something dependent. So the probability of getting a king and a queen without replacement, I do the probability of getting a king, which is 4 over 52. I multiply that times the probability of getting a queen, given that on the first draw I drew a king. We did that on the first page. That was 4 over 51. Oh, yeah. Calculator right up there. So the probability of drawing 2 cards and getting a king and a queen in that order without replacement, is it very likely? No. 0.006, that is approximately 0.6%, so less than 1% chance that that happens.
Okay, so 4 over the 52 is given that you most came through.
Yeah, this is the probability of the first event.
Okay.
This is the probability of the second event, given that on the first try I drew a king. And I kept the card. Questions so far? Okay. So let me ask you this: the probability of a salmon swimming successfully upstream, so fish, a salmon, the probability that it has success swimming upstream is I'll write probability of salmon is 0.85. So you tell me, using the appropriate rule, the probability that 2 salmon swim upstream successfully. Take a second to do that. Hang on, take a second. So do that, like the first, just sit there, now like, oh yeah.
Whatever, right?
I don't know. Ramona, what'd you get? I don't know how to do it. Somebody help. Juju. 0.72. Can you tell me what you did? So how come you just multiply them together? Because why? Are 2 salmon swimming upstream independent or dependent? They're independent. So I could just multiply the probability of 1 salmon swimming upstream times the probability of another. So yeah, and that turns out to be what, Juju? 0.729. So approximately 72% probability. Okay, so we have a doctor spell that right? Okay, so is that two C's? Okay. Mrs. Pickard teaches English. The probability that this doctor takes you in and fixes your knee is 0.85. Pretty good, eh? You wouldn't want the doctor that got a D. So I want you to tell me, you figure it out, the probability that he has 3 successful knee surgeries in a row. Okay, 30 seconds. The probability that he has 3 successful knee surgeries in a row. Wait, hold your applause.
It was already on the calculator when I turned it
At graduation this year, they will say, please hold your applause to the end, and then nobody will listen.
Nobody ever does.
Wait, so real quick, Power's last graduation.
No, I don't.
Would they care? Yeah, would they care? Like, I'm graduating, would they care? Like,
They might not let you walk.
Dude, make them fancy stuff.
Yeah.
All right, by raising your hand, somebody tell me what they did, why they did it, and what they got. Mary.
In this group roll up. At times 85, 300.
Okay, how come?
And I got 61. Yeah, 4125. Yep.
0.6141.
5, yes.
Okay, how come you did 0.85 through 10?
Because you said the succession of 3 in a row, so I just.
Are they independent events or dependent events?
No, I did.
If they're dependent, then I can't just multiply them together.
Oh, I mean,
Aaliyah,
I got 0.59262.
what did you do?
Judging by that, listen, no, it's not very long.
What did you do?
At times 0.85, 0.84.
Okay, so this is right. They are independent because the success on one knee surgery does not depict the success on another. Okay, and it doesn't drop as you go either. This is his success rate, 0.85. Okay, so somebody. I want you to find the probability that he takes the L on all 3. Take like 20 seconds, 30 seconds. Don't shout it out. You can look on your calculator. The probability he takes the L on all 3 in a row. Hannah. Yeah, first tell me what you did.
I just did it up to 0.15 times 3. Or like 1.5.
Okay, how'd you get 0.15?
Because that was probability.
Cool, so if the probability of being successful is 0.85, the probability of being unsuccessful or taking the L is 1 minus 0.85. So then, what'd you get?
0.003.
Cool. So not very likely that he ruins 3 of your lives in a row. One final question for this surgeon. talk too much about taking L's. Yeah, he's done. What's the probability that he gets at least one success? Think about this. Anybody?
Can I tell you what I did? That's my calculator.
Do you have it, Bruce? Yeah. Let's let Bruce try. Go ahead. 85%?
Oh.
0.01.
What'd you do?
So I did time. Oh, 0.15 times 1.5.
That would be the probability that he fails, then passes. But there's more options there, right? He could, at least one means that he could have 2, or he could have 3, or he could have 1. It doesn't matter which one he is successful on, right? The probability that they're all bad is this. So the probability that at least one of them is good, so something goes well, is 1 minus the complete failure. Which is what?
0.996.
So if he goes to, this is called a complement. You might want to write that down. Complement. I think I brought that up before too. So the opposite of failing all 3 times is being successful at least 1. Complement. Sort of like angles that add to 90. So these are events that add to 100%.
Circles are at.
All these are set. All these steps.
Yes. Yep. I have one more example, then we'll try something new today. Yeah. So yeah, let's do a dependent example. Let me read this to you.
No, because I kept them because I was so conscious.
I won't use the reading voice I use for Owen.
What's the reading noise?
More than 15,000 U.S. So we have a lot more than 15,000 U.S. medical seniors. They're all applying for residency programs. Does anybody not know what that is? It's sort of like student teaching. Before you become a doctor, you must. So, of those students, 93% of them were matched with a residency position. So the probability of getting a residency is 0.93. So there were 7% of them who were out of luck. So 82% of those 93% were matched with one of the top 3 choices that they had. So they went and they, I did this for student teaching. I listed the schools where I would like to student teach, and then they sent me where they felt like it. Okay. So 82% of these students who got a residency ended up somewhere they wanted to be. So the probability that they got their top 3, given that they got a residency, is 82.82. So I want to know the probability that a randomly selected senior out of all those medical students was matched with a residency position, and it was one of their top 3 choices. So I want to know the probability of getting a residency and it being a top 3 choice. So go to where you wrote your multiplication rules.
So 0.93 times 0.82.
What's that? So these are dependent events. In order to get into your top 3, you must first have been selected for a residency program at all. So dependent events, for both of them to happen, I take the probability of the first one happening and I multiply it by the conditional probability of the second one happening. So what do I get? 0.76? You gotta speak up.
0.7626.
So that's not bad. Approximately 76% of the seniors ended up where they wanted to be. The rest of them just had to deal with it. What's that?